In this example, we want to classify all critical points of the function g of x is x squared minus 4x plus 1 all times e to the minus x. And by classify here, we mean to determine whether the point is a local maximum, local minimum, or neither. We can do this via either the first or second derivative test, and so we'll do them by both in this example. So we can start by taking the derivatives of this function. So first we take our first derivative, g prime. So I will get x squared minus 4x plus 1, leaving the first part alone, times a negative e to the minus x, we'll differentiate e to the minus x with the chain rule, and then plus a 2x minus 4 times e to the minus x. I can collect these terms together and factor in e to the minus x out of all of them, and from the first I will see a negative x squared plus a 4x minus 1 plus a 2x minus 4. This becomes an e to the minus x times a negative x squared plus 6x minus 5, or pulling out a minus sign from that part, negative e to the minus x times x squared minus 6x plus 5. And we see that this inside part factors, which I will indicate now for the sake of finding the critical points. This factors as negative e to the minus x times x minus 5 times x minus 1. So this factoring here tells me where all the critical points are. So this tells me that my critical points are at x equals 5 and x equals 1 from these two terms. Since e to the x is never 0, I don't get a critical point from that first factor there. Now to classify these by the first derivative test, we can do this right now. We can look at the number line here for the first derivative and see what happens. We should mark points at 1 and 5. And then we can plug in some numbers. If I plug in 0, I will get a negative 1 in front from this term, times a minus 5 times a minus 1, that's 3 negatives is a negative answer, so I get negative down here. If I plug in 2, I still have a negative term in front, that's negative e to the minus 2, that's still a negative number, times negative 3 times positive 1, that's positive. If I plug in 6, I get negative times 2 positives is negative again. So via the first derivative test, I can see that x equals 1 is a local minimum, because it goes down to up at 1, and x equals 5 is a local maximum, because it goes up to down at that point. Now we can do the same thing with the second derivative test, and that will start with having our derivative, which I will leave unfactored because it'll be easier in this case, and then going to take the second derivative. So in this case, we get the second derivative is an e to the minus x times the inside, and then minus e to the minus x times a 2x minus 6. And again, I can recombine terms here. So factoring e to the minus x out front, x squared minus 6x plus 5 minus 2x plus 6 is e to the minus x times x squared minus 8x plus 11. And that here is not going to factor, but I can still use it to figure out if I have a local maximum at my critical points. So to do that, I need to plug my critical points into the second derivative. My critical points from before are at 1 and 5. So g double prime of 1 is e to the minus 1, that is a positive number, that's the important part there, times 1 minus 8 plus 11. That inside there is going to be 1 minus 8 is minus 7 plus 11 is positive 4. Positive times positive is a positive number. This means that by the second derivative test, 1 is a local minimum. We can do the same thing for 5. G double prime at 5 is e to the minus 5, also a positive number, times 25 minus 40 plus 11. 25 plus 11 is 36, minus 40 gives me a negative 5, that's giving me negative times the positive number is going to be negative, and this is a local maximum. So in this case, by either the first or second derivative test, we get that x equals 1 is the local min, x equals 5 is the local max. Those answers will always agree. The only difference is that the second derivative test might be inconclusive. In this case, it wasn't, and we got the same answer for both of them. So if it works, you can use either one to figure out what your critical points look like for a given function.